Welcome back, my friends, to another wonderful video of MRWC. Today we're going to be talking about Chapter 7. Oh, I'm sorry, Section 7. And, there's a whole lot of rational expressions and holes and asymptotes and oblique asymptotes. And all kinds of wonderful, joyful things that we love and enjoy. So let's begin with number 1 here. I recommend that you pause the video and do the problem and see what the explanation is. So we'll be right back. And we're back. Number 1. Would the following have a hole, an asymptote, or both, and why? Well, my friends, you know what the first thing is you're supposed to do? Factor. Okay, so the denominator is already given, basically. But the numerator, x box time, 8 on top, 6 on the bottom. What multiplies to 8 and adds up to 6? Why, 2 and 4, of course. They're all pluses. So this is x plus 2 times x plus 4. Now, what is x plus 2 going to be? Well, if I was to cancel this fraction, this would simply be x plus 4, wouldn't it? But does that mean that x could be negative 2 after all? Like, because if x is negative 2, don't we get 2? If we plug in negative 2, don't we get 2? Well, which one's the real function? The simplified form or the original? The OG, that's right. And so in the original, negative 2 is not allowed. What happens in the original if you plug in negative 2? You get 0 on the bottom. Very good. Unnamed student who doesn't want credit in the video. Negative 2 would make a 0 in the denominator, and we know that's not allowed. And so negative 2 is one of the excluded values. You know what that means for holes and asymptotes? What is it, hole or asymptote for negative 2? Hole. Okay, so this means that there is a hole at negative 2. Let's give it a little color. Okay. Hole. There is a hole at negative 2 because the binomial with negative 2 as a factor simplified away. How can we say this more mathematically? Like, there's a hole at negative 2 because the binomial canceled. I don't know. We'll just say that. Is canceled an appropriate word? I suppose. There's a hole in negative 2 because the binomial, I'll be more specific. Because the binomial x plus 2 canceled. How about that? Okay. And you think we can fit this in on one row? Yeah. Okay. All right. Fantastic. All right. Next up. 1 over x plus 1. Well, in this case, there's nothing to simplify. There's nothing to factor. So we simply have this right here. And what do we think of this? Okay. So this means that what's that negative 1? Hole or asymptote? Asymptote. That's right. Ah, why indeed? Okay, there is a vertical asymptote at negative 1 because the binomial x plus 1 doesn't cancel. Okay, there's no x plus 1 on top to cancel that x plus 1, so therefore there's a vertical asymptote. And that's only for the one in the denominator, okay? Numerators don't give us asymptotes. Numerators just give us zeros, just give us x-intercepts, not asymptotes. So get that straight. There is a vertical asymptote at negative 1 because the binomial doesn't cancel. Okay, good. All right. I think that's good enough. We can move on.
Wait a second.
There's a question, yes?
I got a question.
Yes, I'm listening.
There's a vertical asymptote at -1.
Uh-huh.
There's a binomial x plus
There's
1 doesn't cancel.
There's a vertical asymptote at -1 because the binomial x plus 1 doesn't cancel. That is correct.
How?
Do you see an x plus 1 up top? So what made it cancel on what made the a hole? Why is there a hole at A and not at B?
Oh, does it cancel?
Yeah, see the x plus 2 here canceling? That's why it's a hole.
But that one doesn't cancel.
This one doesn't cancel. That's why there's not a hole. Yeah.
Thank you.
Uh-huh. All right. All right, next problem. I smushed the graphs together in order to save room. So, but they are two separate tasks for number 2. So it says, given the graphs below, describe the behavior around the indicated value. Well, I mean, it's not very profound. I would just say, as x approaches 1, that's an arrow, not a minus greater than. As x approaches 1, comma, f of x also approaches 1. And it's the same from both sides, so I'm not going to say positive, negative, left, right. I'm not going to say any of that because it's the same. So there's nothing very profound here. It's not supposed to be difficult. It's just, it is what it is. And then the second one, we have something a little bit more interesting. Here we can see that it's approaching 2. Sorry, positive and negative infinity as x goes to 2. So what we're going to write, we're going to say as x goes to 2, and you can either put the minus up top, you know, the little exponent minus. I could copy and paste it in, but I'm not interested in doing that right now. You could also use words. So you can say as x goes to 2 from the left. No, from the left, comma, f of x goes to negative infinity. And you can either do that. I have the little symbol too I could use. Let's see here, 236, 236. So I could do like that, or I could use words. I kind of like the symbols, but you know, it's fine. We'll just use the words. Okay, and then as x goes to 2 from the right, f of x goes to positive infinity. And that's all there is. That's all I care. Do I care about the asymptotes at the x-axis? Do I care that as you go left, it goes to 0 from below, and as you go right, it goes to 0 from above? No, I don't care. Not in this one. Not for the way they asked, because they just want the indicated value, that red dotted line there, you know, at 2, what happens at 2. It all depends on the question. There was, yes, a question? Yes, unnamed student? Okay, great. Moving on. Fantastic. What does discrete mean in terms of mathematics and function behavior? What about continuous? Okay. Do you want to share your definition? Okay. Continuous. You said continuous means it keeps on going forever. Continuous means... I actually slightly disagree. Because continuous does not imply infinity, it just implies no break. So continuous means You know, I guess I can't say it any simpler than that. Means no break in the graph. How about that? Discrete means there are disconnected values, like integers, like points. Okay, so like there's if you ask me how many kids I have, those are only given in discrete values. Whereas if you ask me how tall my kids are, there's a continuum of values that I could theoretically tell you, right? Like their height, there's a continuous range of values that I could give you for their height, but for their age, I can only give discrete values because, well, okay, in terms, well, I suppose I could give you a continuous value for their age, but in terms of you asking like how many years old my kids are, in that sense, I have to give you a discrete value. Okay, or I'm sorry, I think I originally said how many kids I have. That is a discrete value, right? So you asked me how many kids I have. I don't have, there's no continuous values of kids. There's only discrete values. There's only integers. Right. Okay. Number 4. For each function, fill in the information in the table. And we have some nice little equations here and lots of fun to be had. I recommend you pause it or maybe just watch it a little bit and then pause it. So x-intercept. Well, so what they want is for you to look at the individual x-intercepts and then say things about them. Okay, so here that's -1. Here that's also -1, and but this one's -3, I just realized. Okay, and multiplicity of root for this one is 1. For this one is 2. It's just talking about the exponent. Okay, for this one here it's 2, and for this one here it's 3. And what does it do when it hits the x-axis? This one here goes through. Excellent question. How do I know that that one goes through? Well, if it has a multiplicity of 1, it goes through. Because that means that, well, I suppose there's a little bit of experience involved. I don't know if I can tell you a better way to know, but if you have multiplicity of root 1, there's no bounce, there's no hitch. It just, it approaches the x-axis without hesitation or delay. It just does its thing. Okay, it doesn't react to the x-axis in any unusual way. Okay, so here though, multiplicity of root 2, that's a bounce. Okay, and this is a odd positive polynomial. So in other words, the graph of this function, if I can give you a little rough sketch, it's at -1, it goes through, and it comes down at 3, and it bounces and it goes up. So what I'm saying is like this is like the x-axis here, and then we could say like the y-axis is like here. Then there would be a bounce, and you could be more specific. You could say, oh, it bounces from positive to positive. It bounces up, but that's really all they want. It's very simple. Same thing with this one here. This is a bounce, and this one, I like to call this a hitch. I'm sure there's other ways to describe it, but that's what I have. Number 5. Check this out. Absolutely, we have time. We have 3 more minutes. Let's go. Quiet, please. Thank you. Thank you. Oh, I know you're excited. Okay. Draw a possible sketch of a polynomial that has all the following characteristics. The domain is all real numbers. The range is all real numbers. You know what that tells me? That tells me odd polynomial. Because odd degree polynomials have infinite domain and range with no limitations. There are 2 x-intercepts, one negative and one positive. Okay, that's not, I mean, it's awfully vague. I guess I could pick almost anything. So, okay, I'll pick like -4 and like +3, I guess. The negative x-intercepts have a multiplicity of 2. The positive one has a multiplicity of 3. Okay. Well, let's just do this then. So the negative one has multiplicity of 2, so it would bounce. And the positive x-intercept has one of 3, so it could give me like a little hitch. And you know what? That's it. That's all it needs. That's like super. That's it. Last one. Write a possible equation for the following polynomials. You want to see it again? Okay, just pause the video and look at it. Okay. Yeah, write a possible equation for the following polynomials function. It has a root of multiplicity. Okay, so these are two different ones. I actually want to look at B first. So this one here is x minus 1, x minus 2, and x minus 4. And there's no bounce or hitch. So, like, that's good enough. This one here at x minus 2, so that's x plus 2. And multiplicity 2, multiplicity 3 at x minus 3. And that's really it. I don't see any other problems here. Thank you very much, everyone. Please like, share, and subscribe. Buy my merch. Have a good day.